Matrix operations. Before we start working with matrices, we would like to describe them. What is a matrix? A matrix is simply a rectangular array of numbers. Here is an illustration. First row, second row, third row. That is a rectangular array of numbers. It has 3 rows and 6 columns. Another example of a matrix is the matrix that has 1, 2 in first row, 3, 4 in second row, 5, 6 in third row. Here is another matrix. First row has 6 plus I, 5i. Second row has 4, 2 minus 3i. Here, this matrix has complex number entries. And this last example is the matrix that has 1 row, 1 column. Its entry is 2. Now we have some notation for matrices. We write a rectangular array, and then we enclose it with some brackets or maybe some parentheses. Okay, next. Matrix dimensions. For positive integers m and n, an m by n matrix, notice the notation, m by n matrix, is a matrix that has m rows and n columns. In this class, when we have an m by n matrix and we name it A, we can denote that by A underscript n by n. This is communicating that you're looking at the matrix whose name is A that happens to be of dimensions m by n. We also have entry notation. So observe here that I have my brackets, and within those brackets I have a subscripted A, ij. I could use parentheses, we could use parentheses, and what that means is that this is the matrix A that has entries aij. Aij denotes entry-wise the entry that is at the 8th location in a row and the j-th location in a column. So AI is located in the ith row and j-th. Aij is located in the ith row and j column of the matrix. So let's turn to the camera to clarify that with an example. Let's say that A is the matrix 1, 2, 3, 4, 5, 6. This is a 2 by 3 matrix. So this is a 2 by 3 matrix. So A11 denotes the entry that's located in the first row and first column. In this case, that's 1. A12 is the entry that's located in the first row, second column, which is 2. A22 is the entry that's located in the second row, second column of A, which in this case is 5. Okay, let's look at these examples. A 3 by 6 is defined to be the matrix whose first row is 2, 0, negative 5, 2, 17, 1/2. Second row is 8, negative 11, 4, 0, 0, 5. And third row is negative 3, 7, 15, negative 2 over 3, 6, 23. That happens to be a 3 by 6 matrix. Notice that our notation communicates that. our notation here communicates that B is a 3 by 2 matrix, and it specifically is the matrix that has 1, 2 as first row, 3, 4 as second row, 5, 6 as third row. It is a 3 by 2 matrix. C is a 2 by 2 matrix. Its entries are C11 equals 6 plus I, C12 is 5I, C21 is 4, C22 is 2 minus 3I. And finally, this matrix A, which is a 1 by 1 matrix, is the matrix that contains the number 2. It is a 1 by 1 matrix. Okay, in this example, number 2, I'm giving a matrix, we are giving a matrix, and then we are identifying its entries. So A11 is a 1, A21 is 0, A31 is 0, A41 is 0, A51 is 0. A21 is 0, A22 is 1, A32 is 0, A42 is 0, A52 is 0, etc. Okay, let's talk about matrix equality. Let A be an M by N matrix. Matrix B is equal to A if and only if B is also an M by N matrix and the entries Bij are equal to the entries Aij. For I equals 1 to M and J equals 1 to N. Okay, let's exemplify. Determine whether the given pair of matrices are equal. The matrix A that has entries 1, 2, first row, 3, 4, second row. The matrix B, which has entries 1, 2 as first row, 3, 4 as second row, 5, 6 as third row. Now we have to conclude that these two matrices cannot be equal because there is a mismatch in the dimensions. So A is not equal to B because A is a 2 by 2 matrix and B is not. Number 2, the matrix A consists of 0, 1, 0, 1, 0, first row, 1, 0, 1, 0, 1, second row, 0, 1, 0, 1, 0, third row, 1, 0, 1, 0, 1, fourth row, 0, 1, 0, 1, 0, fifth row. B, first row is the same as the first row of A. The second row of B is the same as the second row of A. The third row of B is the same as the third row of A. But notice that in the fourth row there is a mismatch. A for 1, A for 5 is 1, but that's not equal to B for 5, which is negative 1. So in that matrix, A for 5 is 1, which is not the same as B for 5, which is something else, negative 1. We have to declare that these two matrices are not equal because there is a mismatch in a case of corresponding entries. A for 5 is not equal to B for 5, so these two matrices cannot be equal. For two matrices to be equal, they must have matching dimensions, equal dimensions, and entry by entry, they must be identical. So Aij must equal to Bij for all I and for all j. Okay, number 3. Notice that in this example we are looking at matrices written in entry notation. So I'm going to copy that and we're going to check. So C, which is a 3 by 3 matrix, is described by the entries I plus j, and D, which is also a 3 by 3 matrix, is described by the entries j plus I. Okay, are these two matrices equal? Well, let's see. C is a 3 by 3 matrix. So let's obtain a 3 by 3 matrix. Now, A11 is described here. This describes Aij. So if you want A11, it's going to be 1 plus 1. 1 plus 1 is 2. A12 is going to be 1 plus 2, which is 3. A13 is going to be 1 plus 3, which is 4. Okay, so that completes my first row of C. Let's get my second row of C. Here I'll have C21. Let me go change it. Let me use C's in here, just to match the name of the matrix. So this is Cij. Okay, so this will be C21. C21, according to the rule, to the definition, to the formula for Cij is going to be 2 plus 1, which is 3. So here I have a 3. There I will have a 4. I will have a 5. Okay, finally, C31. Let's see what C31 is. The formula says that's 1 plus 3, which is 4. So this will be 4. Then this will be C32, which is 3 plus 2, which is 5, and C33, which is 3 plus 2, which is 6. Okay, so there's your matrix C. Now, let's compute our matrix D. These are entry-wise. I'm going to call these entries Dij, lowercase. So D11 is 1 plus 1, which is 2. Now, this is supposed to be D12. D12 is going to be 2 plus 1. Why 2 plus 1? Because I'm adding j plus I. Here j is 2, I is 1. So that's 3. Notice that I'm going to get 3. I'm going to get 4. And if I perform the rest of the computations, I will come up with this result I wrote. Notice that they, in fact, coincide. They are equal matrices. They're both 3 by 3 matrices, and entry by entry, they are identical. In other words, here I get that Cij equals Dij for all. This is the symbol for every or for all. I equal 1, 2, 3. J equal 1, 2, 3. Okay, so in this example, C and D are equal to each other. Okay, so these are equal. Okay, scalar multiplication. When you have a matrix and each of its entries are multiplied by the same number, you call that operation scalar multiplication. So given a constant C, a matrix A, the scalar product of C and A is denoted by Ca and is given by the formula C times the matrix A is simply the matrix of entries that you obtain by multiplying C times each of the entries of the matrix. So Caij. In other words, the Ij entry of Ca is C times the Ij entry of the matrix A. So quick example here. Oh, well, let's say there are examples in our notes. So let's look at that. So A, the matrix A, is 2, -1, 5, first row, and -7, 0, 13, second row. Let's find the 3A. I want to compute 3A here. So 3A, what is that equal to? Well, let's turn to the camera. 3A, by definition, is going to be 3 times Aij, which is I'm multiplying each of the entries of the matrix A times 3. So I'm going to have 3 times 2, 3 times -1, 3 times 5, 3 times negative 7, 3 times 0, 3 times 13. So that's the scalar product 3 times 8. When you do the calculations, that's 6, negative 3, 15, negative 21. 3 times 0 is 0, and 3 times 13 is 39. Okay, I'll highlight this for the audience to try, and then I will show the answer. Okay, so I'm hoping I did not miscalculate any one of those, but the answer for the scalar product negative 2a will end up being 8, negative 4, 20, 14, negative 28, 0, 52. Okay, look at example number 2. 5, 6 times the matrix 18, 16, 14 in first row, 12, 10, 8 in second row. So you have to, to obtain the scalar product, you have to multiply each of these entries, 18, 16, 14, 12, 10, 8, by 5 over 6. So let's do 18 times 5 over 6 to confirm that the answer is what's shown in the notes. Notice that 6 cancels with 18. So you end up with 5 times 3, which is 15. Checks. Let's multiply 5 over 6 times 16 now. 5 over 6 times 16. You can cancel out a 2. So that gives you 8. That gives you 3. Nothing else cancels, so you just multiply 5 times 4, which is 40 over 3. Let's see, 40 over 3. And the audience can check that the remaining multiplications will result in this increase. Okay, 0 matrices. Obviously, when you say 0, you're thinking of 0 entries. So a matrix whose entries are all 0 is called a 0 matrix. Notice that we are saying a 0 matrix because there could be different 0 matrices. Here is the 1 by 1 0 matrix. Here is the 1 by 2 0 matrix, the 2 by 1 0 matrix, the 2 by 2 0 matrix, etc. So if I asked what is the 3 by 3 0 matrix, the 3 by 3 0 matrix, 0 matrices are denoted by the Greek letter theta. So the 3 by 3 0 matrix is simply the 3 by 3 matrix that has all zeros as its entries. Okay, how do you add matrices? The requirement to be able to add 2 matrices is that they have matching dimensions. So you want to add 2 matrices. If one of them is m by n, the other one will also have to be m by n. So that's a requirement to be able to add matrices. So how would you add a matrix A, which has entries aij, and another matrix B, which has entries bij, and they're both matching dimensions? You could say If this is an n by n matrix, that's also an n by n matrix. So how would you add them then? Well, the definition that we are presenting here is you add corresponding entries together. So A11 plus B11, A12 plus B12, A13 plus B13, that's for the first row. And then for the second row is A21 plus B21, A22 plus B22, A23 plus B23, etc. In other words, entry-wise, you add Aij plus Bij. So that's how we add matrices. If you wanted to write this in its full glory explicitly, let's look at it here. So let A be an m by n matrix. This is the explicit expression of an m by n matrix. M rows, n columns. B is also, so let B also an m by n matrix. So here we're denoting a matrix B with m rows and n columns. So how do we add them? Well, we do the following. We get another m by n matrix. The result is a matrix with m rows and n columns. And the entries are, to get the first entry of the resulting matrix, you just add the first entry of each of the component matrix. So A11 plus B11, A12 plus B12, A13 plus B13, and so on, up to A1n plus B1n. Let me repeat that. A1n minus 1 plus B1n minus 1, and then A1n plus B1n. And then the second row of the result is A21 plus B21, A22 plus B22, A23 plus B23, and so on, up until you fill all the m rows and n column, m rows and m rows and n columns. Excuse me. If you want to subtract, the process is pretty much the same, but now instead of adding entries, correspondingly you are subtracting entries. So if you want to take the, if you want to find the matrix A minus B, then you will say Aij minus Bij in all cases. Okay, let's continue. Also, here is the entry notation for addition of matrices and the entry notation for subtraction of matrices. Okay, let's do an example. So simplify. I'm going to copy this and we're going to work it out on paper. So simplify 2 times the matrix 1, 2, 4, 8 minus 3 times the matrix 3, 4, negative 2, negative 1 plus 5 times the matrix 1/5, 3/5 in the first row, and then 7/5, 9/5 in the second row. Okay, so there is an order of operations when you are performing matrix operations involving addition, subtraction, and scalar multiplication. It is the scalar multiplication that gets done first. So I have to take care of this 2 times that matrix, 3 times that matrix, 5 times that matrix first. Okay, so 2 times the matrix 1, 2, 4, 8. What we do is multiply each of the entries by that constant too. So you obtain 2, 4, 8, 16. Okay, now we're multiplying 3 times 3, 4, negative 2, negative 1. So 3 times 3 is 9. 3 times 4 is 12. 3 times negative 2 is negative 6. 3 times negative 1 is negative 3. Okay, so now 5 times our third matrix. So 5 times 1/5 is just 1. 5 times 3/5 is just 3 because the 5's cancel. 5 times 7 over 5 is 7. And 5 times 9 over 5 is 9. Okay, so my scalar multiplications are complete. Now what I'll do is I'll do my addition subtraction from left to right. This should be familiar. That's how we add, subtract a real number. So order of operations remains the same for addition of matrices. Okay, so here I'm going to subtract. Remember that is Aij minus Bij. This is Aij and this is Bij's. 2 minus 9, 4 minus 12, 8 minus negative 6, which becomes 8 plus 6, and then 16 minus negative 3, which becomes 16 plus 3. So the result is what? 2 minus 9 is negative 7, 4 minus 12 is negative 8, 8 plus 6 is 14, 16 plus 3 is 19. Okay, so that took care of that. Hopefully I have not made an arithmetic mistake, because then I will have to go and correct it. Okay, now I add. So negative 7 plus 1 is negative 6. Negative 8 plus 3 is negative 5. 14 plus 7 is 21. 19 plus 9 is 28. There is nothing here. That's a mistake. Okay, so let's see. Negative 6, negative 5, 21, 28. Okay, so it looks like this went well. All right, let's introduce the dot product. This will be our last item in this video. A subsequent lesson, a subsequent video will continue after dot product. So given an 1 by n matrix A and a n by 1 matrix B, their dot product is A dot B is given by this combination. So let's see if we understand. Let's try to understand what the result, how we are obtaining that result. So A dot B, sometimes we simply say AB, but strictly speaking is dot. So A dot B, the dot product of A and B. The dot product of A and B. That's how you pronounce this. You end up contracting it to A dot B. Okay, so here's what you do to get the dot product of A, which is a row matrix. This is called a row matrix. And B, which is called a column matrix. What you do is you take the first row, the first entry of the first row, and multiply it by the first entry of the row of the column matrix. So A11, B11, A11, B11. And then you say plus, and then you multiply the second entry of the row matrix times the second entry of the column matrix. So you multiply A1, 2 times B21. And then plus again, and then you multiply the third entry of the row matrix times the third entry of the column matrix. And so on up until the last entries. So the last entry of the row matrix times the last entry of the column matrix. Notice that both matrices have to have n entries, and that's why we are specifying in the hypothesis. A is a 1 by n matrix, and B is an n by 1 matrix. So this one has n columns, that one has n rows. So the match is there for this calculation to be possible. Now, using sigma notation, The dot product of A and B is simply the sum from I equals 1 to n of A1I, BI1. Okay, some examples. So find the dot product of the matrix A, which is a row matrix, 2, -5, 12. In the matrix B, which is a column matrix, 7, 3, -2. So I want A dot B. Okay, so 2 times 7, which is 14, plus -5 times 3, which is -15, plus 12 times -2, which is -24. From left to right, 14 minus 15 is -1. -1 minus 24 is -25. Okay, and we know that's the answer because it was written in the notes. Okay, so example. Find the dot product of the matrix A, which is 1, 2, 3, up to n, and the matrix B, which is n minus 1 and minus 2 down to 1 as a column. Okay, so this problem turns out to be a little bit tricky because n is an arbitrary integer greater than or equal to 1. So if n is 1, of course, you just get the answer 1 times 1, which is 1. If n is 2, then you get 1 times 2 plus 2 times 1, which is 4. But then what we want to know is what do we get for n in general. So in the next page, we're going to see the patterns that are going to help solve this problem. So the dot product is 1 times n plus 2 times n minus 1, 1 times n plus 2 times n minus 1 plus 3 times n minus 2 plus plus n minus 2 times 3 plus n minus 1 times 2 plus n times 1. Okay, so now observe the following. We're going to look at each of the bottom entries. So the bottom entry here is n. The bottom entry there is n minus 1, n minus 2, all the way down to 3, 2, 1. We're going to look at each of those as n plus 1 minus something. So n is also n plus 1 minus 1. n minus 1 is also n plus 1 minus 2. n minus 2 is also n plus 1 minus 3, and so on. Now, what about 3? 3 is n plus 1 minus what? Well, it's n plus 1 minus n minus 2. Observe that the n's cancel, and the 1 minus -2 gives you 3. And then you fill in the other one accordingly. So n plus 1 minus n minus 1. The n's cancel, and then 1 minus -1 becomes 2. And then the last one is n plus 1 minus n, which will give you 1. Now, observe that with this pattern, you can multiply by distribution. So 1 times n plus 1 minus 1 times 1. So I'm doing this. On the top, I'm putting this result. I'm putting the result of 1 times n plus 1. And here on the bottom, I'm putting my minus, and then 1 times 1, which is 1 squared. We know it's 1, but I want to see a pattern here. Now the second one, plus 2 times n minus 1, and then minus 2 times 2, which is 2 squared. So 2 times n plus 1 minus 2 squared. And here 3 times n plus 1 minus 3 squared. Notice that this pattern goes all the way down up to the end. So this increases 1, 2, 3 times n plus 1, all the way to n times n plus 1. And then each of these increases to minus 1 squared, minus 2 squared, minus 3 squared, minus that, minus n minus 2 squared, minus n minus 1 squared, minus n squared. So that's what's going to happen when you do these distributions right here. This distribution, that distribution, this distribution, that distribution, this distribution, that distribution, all the way. So that's the pattern that arises. So what you end up finding is that in this top calculation, you can factor out the common factor n plus 1. So you get n plus 1, let me highlight that, times 1 plus 2 plus 3 plus plus n. 1 plus 2 plus 3 plus plus n. And then on the bottom here, you can factor out that big minus. So you get minus 1 squared plus 2 squared plus 3 squared plus plus n squared. Now, as it turns out, if you think back to an algebra course, to a previous algebra course, like pre-calculus algebra, you will remember that this sum 1 plus 2 plus 3 plus plus n happens to have a formula, n plus 1 over 2. So you end up with what you already had, this n plus 1, times whatever this fellow gives you here, which is n plus 1 over 2. And then this formula is one that not many students remember, that is formula for sums of squares. Let me show you that from the previous page. So when you add the perfect squares from 1 to n, you get this result, n plus 1 to n plus 1 over 6. Let me remark that in this page I'm providing various finite sums. So if you add a 1 n times, you get n. If you add 1 plus 3 plus 4 plus that plus n, you get n plus 1 over 2. If you add 1 squared plus 2 squared plus 3 squared plus that plus n squared, you get this result. And then there is here the cubes, 1 cubed plus 2 cubed, etc. There is also a formula for that. For anybody who's taken a calculus class, these do come up in there. For us, I'm listing them here in page 7 of the notes. Okay, so at any rate, I'm going to take this formula right here, and I'm going to use it in the sum of squares that's down here. So that's going to be n plus 1 to n plus 1 over 6. So after you do some algebra, adding subtracting fractions, denominators have to be the same. So you multiply that one by 3. And then you do some factorization of common factors, you get this cute formula right here. So when you take the dot product of those two matrices, you end up with this neat result, n times n plus 1 times n plus 2 over 6. There will be some exercises that are associated with this in some homework exercises. Okay, I think this is good enough for now. So that's all. Thank you.